So I now want to introduce our speaker tonight. This is Dr. Crosby's second talk for us. The first was on changes in Alaska due to climate change. Dr. Crosby is a native Californian. He is currently the department chair at Idaho State University in Pocatello. He's been a professor there for 15 years, and his initial education, he has a bachelor's degree in geology from University of California, Berkeley, and then moved across the country to get his PhD from MIT. He has held positions at UC Berkeley, Lawrence Berkeley National Labs, worked with the National Park Service up in Alaska, also with MIT, Harvard, and like I said, the last 15 years at ISU, where he's a professor and has a full range of teaching duties, as well as numerous graduate students that he has shepherded through the process. And so I know you don't want to hear from me. I'm going to turn it over to Dr. Crosby, and let's hear about landslides in the Tetons. Thank you, everyone.
Awesome, Mike. Thank you so much for the introduction. And I'm really excited to bring this work to this group, especially since it is a project that is in progress. And I have a current graduate student, Josh, who is putting a tremendous amount of work into this right now, but still has a year plus of time to continue working on the project. And the kind of feedback and discussion that we might have tonight will end up being quite valuable for focusing and continuing the sort of applicability and value of a project like this that has sort of a public-facing component. The intention for tonight's talk, I'll share my screen just so we can start having some visuals, is to introduce to you a number of different aspects of landslides, the data sets that we're working with, as well as some of the initial findings in this project. And I think that being able to bring everyone up to speed on how we do what we do is as important as getting into the nitty-gritty details of what's been done so far. And I do see that Josh is on the call, and so I hope that as we get into the discussion, there's opportunities if folks have questions for Josh and his process, that he can be included as well. And as you can see on my title slide here, it's clear that at the bottom, much of tonight's work comes through efforts by Masters of Geology graduate students, Josh, who this is dedicated 2 years of his life to doing this. And Kyla Grasso was also helpful in getting this project off the ground a couple of years back. And so they definitely deserve a lot of credit for helping move this project forward. So I like to think about things from a big picture perspective. And I like to start with a motivation. And why bother studying landslides? Well, certainly they abound. And this is true globally, as well as within this field area. And that landslides are important to understand because they have the potential to cause harm. And that harm can be both to individuals, it can be to groups, it can be to infrastructure, and other valuable resources that are important for not just individual health and safety, but also for the economic well-being of a place like the Jackson Hole Valley. And I think that it is important to be aware of them so that you can make sort of the best management decisions possible. One thing that is special about landslides is that they tend not to come from nowhere, right? They don't come out of the blue. They are often recurring. And so being aware of the past presence and abundance of landslides within a given field area is a great way of being able to anticipate what future landslides might occur. And so this fourth bullet point down about landslides being mappable is really valuable. They are becoming ever more mappable as higher resolution topographic data sets like LiDAR become available. And in particular, oops, I've already got a misspelling on my slide. There we go. And back to this. Grand Teton National Park has a LiDAR data set that I'll detail here a little farther along. That is a perfect backdrop or foundation for being able to observe where landslides occur in the park and characterize them. One of the shocking things when I first delved into doing this project was discovering that though there have been small patches of observations of landslides within the park, some projects within a few canyons, the Wyoming Geologic Survey is in the process of making surficial geologic maps, which do include landslides, but there is no park-wide systematic inventory of the landslides in the park. And so I saw that as a great opportunity to take advantage of an extremely powerful resource like the LiDAR map, and to provide a product that would be valuable not only to the park and their management, it could also be valuable to other researchers and those interested in understanding relationships between, say, mountain building and landsliding, or glacial retreat and landsliding, or numerous other sort of scientific research problems that could be addressed with an inventory like this. But foremost, and this is the last bullet on this slide, that it's really important to share the data and to be able to put our findings out there for the public. And we'll really wrap up tonight's talk with talking about a mechanism for being able to do that. And this sort of democratization of the data, sharing the data out to the broader public, gives the public an opportunity to not just learn something about how the earth works and how mountains fall apart, but also to be able to make decisions for themselves about where they might choose to camp in the backcountry, or the kinds of terrain they might encounter while traveling in the park. So that's the big motivation for tonight. The image that you see here, you'll see it a little farther on and credited. This happens to be the Devil Slide. It's a LiDAR image showing the extension of a large earth flow and slump that expanded across a floodplain in the state of Washington. It just happens to be a great depiction of the kinds of visuals that are possible with these high resolution topographic data sets. I'm a teacher first and foremost, and that's where my passion is. I do love the research that I do and the opportunities that it has to be able to generate products that are communicated out to the research community and help inform decision making. But I'm a teacher foremost, and one of the things I like to do is let you know where you're going to end up by the end of tonight. So by the end of tonight, you should be able to know how landslides work. You should know the value of landslide inventories and sort of what they are. You're going to know about what LiDAR is and how it works. You're going to be able to know something about how LiDAR is, well poised, or essentially the primary tool for high quality landslide mapping. You'll know what motivates using that tool. And then when we get into our data set, you'll become familiar with the LiDAR data set for the park and what we're starting to see in terms of the distribution and character of slides within the park. We'll get into a discussion about patterns that are observable between landslides, bedrock, and topography within the park. We'll get into this discussion about how to communicate an inventory back to the public, and then discuss in closing, and I'd love to hear your ideas as well, opportunities for continued study. As you know, this is a work in progress, and I value all types of feedback. And just as a short aside, I did my PhD on the North Island in New Zealand. I was focused on understanding waterfalls and how they retreat upstream. And I had very, very little money to be able to fund the project. And I essentially flew over there largely by myself. I stayed and worked at a ranch there on the North Island. I made beds, helped cook dinner for a guest stay there. And I was able to convince many random people to come and be my field assistant. In fact, I would go and put up flyers in the local hostels that the tourists were passing through. And I would put up a sign that said, you know, come help me map waterfalls in the bush, and I'll pay for your beer, dinner, and transportation for week-long chunks at a time. And I had some of the best insights while working on my PhD in having conversations with people that were non-scientists, non-geologists, because they were able to go in the field, understand what it was that we were trying to understand, and to be able to throw out ideas and questions that really prompted innovative thinking. And so I look forward to all of your ideas and innovative thinking that you might bring to Josh and I while we're mid-project. Okay, what's the deal with landslides? Well, gravity pulls at everything. And that is true no matter where you are. And for all objects that are out there, there are both stabilizing forces that hold things in place, but then also mobilizing forces that tug at and pull at things. And this is true for my lava lamp sitting on my desk, the pen that's sitting right here, as well as in the image that you can see the side of the mountain that doesn't happen to have a rock fall occurring on it at this moment. You know, you can see that there are stable areas of the mountain that aren't going anywhere. And that's because even though gravity is pulling them down and there's shear on those surfaces that are trying to move things down, things like the friction and the resistance of the bounding areas of rock that are adjacent to it inhibit those objects from moving at most of the time. And it's really only under certain conditions when we might find that these stabilizing forces are exceeded by the mobilizing forces. And that's typically because there's something that comes along that adds energy into the system to move the material beyond some threshold for stability and allow it to fail. And really what the form of the failure is, how landslides occur, how mountains fall apart, is really dependent on the things listed here, the material properties of the mobile material, the topographic setting that material is poised within, and the environmental conditions at the time that it's able to move. And when I say environmental conditions, I've got here marked water as an important driver of potentially destabilizing material, but also energy as well can be added to the system that can cause destabilization. I'm sure in this region, most people are familiar with the idea of the Hebgen earthquake. And the Hebgen earthquake that occurred, I guess it's 30 years ago now, or no, 50. It was just the 50-year anniversary, if I remember correctly. And that was an earthquake that led to shaking, which then caused destabilization of a mountainside, which collapsed down into a valley, wreaking havoc on folks that might have been camping there and spending the time there. And so that landslide is a great example of something that was stable under normal conditions, but when added a little bit of energy to it, was able to cross the threshold and mobilize and fail in them. So if we're going to talk about landslides, let's build our vocabulary. And I know that geojargon is rampant in the world. And unfortunately, the world of understanding landslides is not necessarily devoid of that same jargon. In fact, it is rich in jargon. But I hope to break that down for you today so that you get a sense of what I'm talking about and why it's important to distinguish between these different kinds of movements. So first of all, I'm now going to transition from using the word landslides a lot. And the reason why is that landslides, though a generic term and probably the term you're most familiar with and what you'd see on the news or in a newspaper or in a casual conversation, from a scientific perspective, we describe landslides and we use an umbrella term called mass movement. Right? So that's the big umbrella term that we use to describe when things are mobilized under the influence of gravity and move from one place to another. And when we classify mass movements, there's a classic architecture for doing this. And that was originally proposed by Varnes, referenced down in the lower corner there, Varnes in 1978, and has been subsequently elaborated on and improved upon, but really it retains the same structure that Varnes proposed way back when. And ultimately, what that is that there is a style of movement, you know, exactly how is the material moving, and what is the material? What is the type of material? Okay, so we're going to sort of break that down. So let's start with understanding the style. And so over here on the left side of the table are these different names: falls, topples, slides, flows, spreads, and complexes. We'll talk about complexes in a little more detail in a second here. So, and you can see that there's even subcategories for slides and flows, which are described as translational or rotational. And flows themselves can be broken down into whether water serves as the pore fluid that sort of dilates and moves the grains apart from each other so that they're able to move past one another and not be bound up and locked together. Or air might be that pore fluid. Okay. So, and then under really slow flowing conditions, we might have their own term for describing that, which is creep. Okay, so these are the different styles, and I'm going to show you diagrams that gives you visuals for what these look like. So if falling, toppling, sliding, and flowing and spreading are still things that you're making sense of, don't worry, we will return to them. If we can describe the style of movement, the sort of kinematics of how things are moving, we also need to describe what's moving, and that's this type of material over here on the side. And in this category, the classic breakdown is to describe them in terms of what the grain size is, the size of the material, how easily it's broken down into finer particles, whether it's all one size or whether it's a mixture of a number of different sizes. And we tend to break those down into three categories. And you'll notice that they are the sort of prefix in front of each of these different terms, that we have rock topples, we can have a debris topple, and an earth topple. And they're pretty self-explanatory. Rock is largely composed of coarse, rocky debris that is more at the larger scale and does not have really a mixture of fines within it. For debris, it has much more of a mixture of fines and coarse material. You could think of it as soils or sands or clays mixed in with blocks and other things like that. So debris has much more of a mixture of grain sizes, including fines. And then on the earth side of the materials, we're talking about things that are largely in the sand to silt size. There might be gravels that are in there. There might be the occasional coarse class, but it's largely composed of finer materials. You could think of it as like an earthy, kind of soil, or an aeolian, dusty, sandy deposit, or something like that. You'd expect to see a finer grains, more of a soil-like texture. Okay, so these are the materials. And I promised you that I would talk about complexes. And so right at the bottom right here is complex. And you'll notice that complex is not really fitting into any one category. It's not really a particular style of movement, a kinematic kind of movement. It's not really a material. And in fact, what it is an amalgamation of multiple styles and materials, typically spread out over time. In an earlier slide, I mentioned that landslides reoccur, right? That they don't just sort of happen once. Typically, a slide might occur and then that destabilizes another area and another slide occurs adjacent to that. And even in an individual moment in a landslide's failure, you might see that it starts out as one kinematic style, right? It might start with a slide, a translational slide where a block moves down some surface. But as that block moves, it disaggregates and falls into smaller pieces. And as it moves faster and travels down a valley, as it routed and energy is maintained, it can actually begin to move from being a translational slide into being something with flow-like characteristics, with maybe water or air as a pore fluid, and that leaves behind a deposit that has really flow-like structures over the top of it that looks like maybe what you would expect of if you had poured molasses or syrup or shampoo onto a sloped surface, that you would see sort of flow lines within it like it was moving as a liquid. Okay, so complexes are when you have a mashup of multiple kinematic styles and potentially materials. And that's why it spans all the way across the bottom there. Let's look at some visuals. Okay, so same sequence that we saw before, same orientation. So we have our movement types listed here along the left side, and I'm going to animate this slide so that it moves up in just a second. And then you'll notice that we go from rock, debris, earth, the same sort of material properties that we saw before in the previous slide. And so in any given category, in a particular geologic environment, a fall, which happens to be a vertical dropping of material from a steep face that doesn't necessarily slide, it translates largely vertically to a depositional apron, often right at the base of where the material is sourced from, can occur within solid rock, like shown in this diagram. It could occur within a mixture of materials, of debris. So for example, you could imagine if you had a big, thick, alluvial deposit or something like that, that was piles of cobbles and sand and things like that, that if a river bluff failed or something like that, that you could have more of a debris style material that would be moving and falling off of that bluff face. And then if you had fine soil on that same bluff, let's say it was composed of, the finer outwash materials or something like that, you would expect to see a more earth fall type of a landslide. And so as you look across these different features, and I'll actually erase my sketching here so it doesn't conflict with the animation, but you'll notice that topples occur within rock, topples can occur within debris, they can occur within earth. Topples are where you have a rotational movement of a block that collapses down. The difference between the rotational and the translational slides are really about the plane on which movement is occurring And so in the rotational slide, you have material that is sliding down and away along a failure plane. And you can see that that's echoed again in the debris as well as within the earth material. For a rotational earth slide, you might expect to see multiple different concave flow paths leading to a very hummocky sort of surface of what has moved. Translational tend to be materials that are moving along oftentimes a plane. And oftentimes those are related to bedding, but they can be independent of bedding as well. So they could be, for example, all of the soil or colluvial material that might be piled on top of bedrock might slide along that bedrock surface, even if that surface is not actually a bedding plane. It can just be the contact between the fill of material that's sitting on that slope, and that material might translate down along that contact between the soil, the regolith, the mobile material that's on top, and the immobile bedrock material down below. All right, need to go back and erase again because I got so excited. Let's see, mouse please. There it is. Erase that. Okay, I'll just slide this up a little bit. There are spreads. Spreads typically occur in really flat environments where there might be saturation of especially fine-grained materials. These tend not really to occur there are very seldom rock spreads that occur. Tends really just to be a fine-grained thing, often occurring at the shore of a lake, at the edge of a river, places where areas saturate, and then at very low angles, they slide out toward that open area. They move, they spread out toward open spaces, like the edge of a lake. Flows. So flows listed here compared to the previous one are largely the ones that are driven by saturation by water. And so you can see there's listed a solufluction flow, debris flow, an earth flow. In all of these cases, you have water that is serving as a lubricant that is pushing apart the individual grains and releasing some of that frictional tension between the individual particles and allowing them to move independently of each other. And the other flows that were listed on the previous slide included air as a pore fluid, where you might see the word avalanche being used. Right? Avalanches, we're not talking about snow here, right? We're talking about where rock moving down the side of a mountain has so much energy that it entrains air that actually provides some of that spacing and that dilation, that spreading between the individual moving particles so that it can travel much, much farther. There are numerous examples of this happening in steep mountain environments. And then, of course, our complexes down at the bottom. And you can see that they are named, you know, using the multiple terms, a slump, earth flow with rockfall debris. And this is a composite, rotational, translational that grades into an earth flow at the toe. And I'm going to cut to the chase on this and honestly tell you that for the most part, complexes dominate the natural landscape. And that's because materials change their characteristics as they are broken up and move and are displaced from their original position as they move downslope under the influence of gravity. And that causes them to change grain sizes, that causes them to change the kinematics of how they move from sliding to, say, flowing, or from falling to flowing. All of those types of things can happen. And with the reactivation idea that I spoke of before, when you have a landslide that moves once, well, it weakens all that material, and then it may move again on some of those planes of weakness. But if it moves again, it may move using a different style. All right. So now you know what landslides are. Now you know sort of why they're worth digging into. Let's get into mapping them. Okay. And so didn't mean to do that. So mapping landslides can be done in a variety of different fashions and have been done so for, I'd say hundreds of years. People have been observing and trying to describe and understand landslides. And so the image that you can see right here is Josh Lingblom, my master's student, standing along the Porcupine landslide, which got a ton of press a couple years ago when it flowed in off the side of the mountain and dammed the Grays River, creating a big pond behind it, closure of the road. And Josh is standing out there with a GPS, and he's measuring some monuments as well as the headscarp for the landslide, which is still there and still moving along, even though it's been largely remediated. He's conducting a field observation. He's got boots on the ground, making direct observations. And that's great. You can dig in deeply to understanding, why is the landslide moving? What sort of materials is it made of? Does it remain active? What are the sort of detailed characteristics, the hydrology in the region adjacent to it? Are there springs that are feeding water into that area? These are the kinds of things you can do when you got your feet on the ground. The hard part about it, right, is that when you are doing local field observations, you actually have a very limited scope of observation that you can do. And so field observations are great, but limited. Another way that landslide mapping has been done before in the past is by grabbing some existing maps. So for example, you could grab a 7.5-minute quad from the USGS, a typical map like you see in this image right here from King County, Washington. And you might look at the contour lines on this map and say, you know what? I think I see a deposit down on the bottom. That's the yellow blob. I think it would have been sourced from up within this watershed. I see something that looks like a source area, a headscarp or something like that. And so I'm going to look at these contour lines and infer that there's likely a landslide that existed in this area based on the topography observable within either existing contour maps or DEMs like the 10-meter USGS DEMs that have been made based straight off of those contour maps. The nice thing about it is that it might be a coarse observational tool, but they are extensive. Right now, you can look anywhere you want in the United States in the contiguous zone, and you'll find 10-meter resolution data that gives you a good sense of where some of these deposits and sources might be. Okay. The next level of sort of precision and data that you might pull from in mapping landslides is going to be aerial photography. And in the diagrams that you can see here, a plane flies over. As the plane flies over, it shoots photographs looking straight down. Those photographs are taken with a relatively high frequency so that the photographs overlap with each other. And the plane flies one direction, turns around and flies back right next to the previous swath, turns around, flies back the other way, and literally crisscrosses like you're mowing the lawn, taking photographs of the ground surface that overlap. You can then put those photographs under something like a stereoscope, the image below, and when you look at the two images separated using mirrors, looking into the lenses and using mirrors, you can see essentially the landscape as if your eyes were in the sky and the three-dimensional topography pops out at you. And this is great. This is probably, of all the landslide maps that exist in the world right now, the dominant source for those landslide maps is from interpretation of stereo aerial photographs. And that's fine. Aerial photographs are amazing. They can come in all different resolutions. The plane can fly low to the ground, and you can have really high resolution imagery that you can use to identify different landforms. But the problem is that if there are trees, you don't really see what's going on underneath there. And that brings us to our fourth and final landslide mapping technique, which is LiDAR. And I'm going to go into detail about what LiDAR is and where the data comes from in just a second here. But I want to explain that LiDAR, and this is our title, or our first slide right here, enables the construction of high resolution, bare earth topography, meaning that you can see through the trees. And these two circles that are shown here are the same place. You can see the meanders in the river. They are the exact same location. This comes from a story map called the Bare Earth, which I'll reference shortly. But you can see the difference between these two images. You'd never notice that there was that broad extensional lobe of that landslide heading out across that floodplain if you were just looking down at the aerial photo. All right, so these are the different techniques that folks use. Why do we make landslide maps? Well, we're going to make an inventory, right? The inventory is sort of the foundational bedrock of understanding the role of mass movements within a given landscape. Okay, so everything starts from the inventory. You got to make a map that shows where what is. Okay, so in this particular circumstance, you could think of it like a census of all the past landslides or even presently active landslides that exist within a landscape. All right, and it's useful for both research and land management. And to make a landslide inventory, the secret is that you want to identify scars or deposits of mass movements, right? And these are landforms. You're going to be seeing bumps and wiggles and lines and breaks that are indicative of mass movements. And you can do those using LiDAR data. That's totally possible. That's the images that are shown here on the side. One without the inventory shown on it, the arrow, and then once the landslides have been identified. This happens to come from Oregon's Department of Natural Resources, or DOGAMI. And you can do these kinds of identifications via the methods we talked about before. You can observe it in the field, you can see it in aerial photos, you might see it on a map, you might see it in LiDAR data. You identify some landforms. The big step is once you go from identifying landform to interpreting it as some sort of a mass movement. Is it a slide? Is it a slump? Is it a spread? Is it a topple? How do I affiliate a given landform to a particular kind of movement? And that is where interpretation comes in. Science is constructed from observations, which everyone here in the room, we would look at something and we would agree, I see a bump, and the bump is this long, it's this tall, it has this. How we ultimately affiliate that bump to some geologic or geomorphic process is an interpretation, and thus subject to, different people seeing things differently. And so we have to be honest about when we're observing and when we're interpreting. Okay. So we interpret the type and character of each of the mass movements in the map. And then we're going to look at what the abundance and distribution are of those mass movements within a given landscape. And then we're going to look at a further step is to analyze for patterns and statistics of those different landforms to generate second order products. And those second order products would be a susceptibility map that might show, where landslides are likely to occur and less likely to occur, more likely, less likely. Hazard maps that might show where you would expect landslides to be active within a landscape. A vulnerability and risk map is going to be making an assessment of whether or not there are interactions between these physical processes, those are the hazards, and infrastructure or the presence of humans, right? Or other things that could receive damage, right? That once we start thinking about infrastructure and people, then we're talking about vulnerability and risk. When a natural hazard has the capacity to influence individuals or infrastructure, now we're talking about vulnerability and risk. Okay, and then once these products are generated, we can distribute those to the public and to managers. And really in this project, because this is the first brush at ever making an inventory for the park, we're going to stick to an inventory. I'm not building a susceptibility map. I'm not building a hazard map or doing any sort of risk assessment for the park. This is first order observations. I really look forward to doing those things in subsequent projects. But for right now, We need that bedrock of a solid inventory in order for us to move forward. This is what inventories look like. So here's an example of a landslide inventory. And you can see there's a LiDAR base map that shows really high resolution topography, a number of different polygons or colored blobs on here that show the different types of movements according to their colors. The headscarps are the place where the landslides initiate, and then maybe some sub-scarps or breaks within the mass movements as they move down the slope, with a bunch of descriptions along the side. This is what a landslide inventory map typically looks like, and Josh and I really aim to produce something like this for the park that has all the different features on it. It will be, of course, at an enormous scale because it's such a large area, but we're aiming to create something like this also with a digital component so that you can zoom in and see the details in a particular place, even though on a map sheet, you might not be able to see the details. All right. Setting landslides aside and delving into LiDAR briefly. LiDAR is very similar to radar in that it is a tool that is useful for sending out energy, and that energy bounces off some sort of an object and returns to you, and you measure a distance. It's a time of flight tool. And with this particular time of flight tool, instead of sending out radio waves, as we do in radar, we send out light, pulses of light. And in the animation that you can see here, there's a plane flying over and a laser sweeping back and forth across the landscape, sending out a pulse of energy. That pulse of energy bounces off of anything that it hits along the way, power lines, the tops of trees. And if it penetrates all the way through, like the dappled light that you would see on the forest floor, it makes it all the way to the ground surface, bounces off of the ground surface, returns back to the plane, and the distance between the plane where the laser is sourced and the ground surface is measurable, and thus we know the elevation of the ground surface if we know the position of the plane. Okay, so plane flies over, sends out pulses, which you can see here in these different dashed lines. Those pulses bounce off of the top of the vegetation. That's what's known as first return, as well as bounces off the ground surface, which is called the last return. And the pulse comes down, strikes the ground surface, goes back to the plane. The plane records where the laser was striking the ground and what that distance was, between the source and the bounce. Okay, and from that, we can then make really detailed maps. And the images that are shown here, we got aerial photograph, we have a first return LiDAR that shows you all of the treetops, and then we have exactly this same scene with the trees removed. And so you can see through to the details of the river and the forms of the hill slopes. If you are interested in digging into learning more about LiDAR and landslides and other geomorphic processes, this website called the Bare Earth, which is what's called a story map, is done by the Washington Department of Natural Resources. It's an amazing resource. If you just Google the Bare Earth, you will find it. And it has an amazing set of LiDAR images. Honing in on our backyard. What LiDAR is available within our region? And so you can see right here on this map, we got Jackson right in this location. Here's Teton Valley over the side in Idaho. I'm somewhere down here in Pocatello. And we got, the Palisades Reservoir here, Jackson Lake here, and this is the border as we transition up into Yellowstone National Park up there. And there are a number of different data sets that exist in the Jackson Hole area. The one that I'm going to focus on was flown in 2014. Oops, way too far ahead. Was flown in 2014, and it is the largest of all of the ones in the region. It covers around 1,500 square kilometers. It's 8.8 billion points with a spacing, essentially how many measurements are on the ground in a square meter, has about 5 or 6 points in a square meter of actual elevation measurements. right? That's really high resolution data. That's really fantastic. And there are prior measurements of the ground surface that were done before using LiDAR. So for example, this one in the lower corner is the Teton Conservation District. The little skinny one that's out here is for the Snake River. And then the one that's sort of a sideways smile right at the base of the range, this one is for the Fault Scarp. And if you've been coming to this group for a while, SCARP, there we go. You've probably seen talks by Glenn Thackeray in our department here at Idaho State University that's done a bunch of work mapping that Fault Scarp. So there's great overlapping LiDAR data. The Parks is the newest, most extensive, and has really the best opportunity to do something like this. I do want to also just say, even though it's not a part of Josh's project, I've been using the Teton Conservation District's LiDAR dataset in my geomorphology classes for years now, because there's a whole fantastic suite of landslides that are observable within that region as well. It doesn't mean that landslides are just restricted to the park. That's absolutely for sure. And all of these data sets publicly available today. You can go download them from a website called opentopography.org if you want to get into this. Okay, let's dig into this 2014 data set. All right, so the national park wanted to fly LiDAR. They contacted the USGS, who then contracted a company called Wolpert, and Wolpert mounted a LiDAR sensor to their plane, flew over the park over 2 weeks in the fall of 2014, and delivered back a data set with an accuracy of less than 15 centimeters in the vertical and less than 10 centimeters in the horizontal in terms of where their spots were measured, where the points were that they measured. They then hydro flattened all the lakes and streams because the laser doesn't reflect off of water. It penetrates that, doesn't give really good returns. And so they flatten the lakes to make flat surfaces like Jackson or Jenny. The data set includes the elk refuge as well as the Rockefeller Parkway. So it's not just limited to the park formal. And then this is of course valuable for numerous purposes, from management to doing geosciences to understanding things having to do with ecology or meteorology even. So I want to start out by showing you some of what this looks like. So this is an aerial photo. We're looking at a straight down or nadir view, looking straight down at the area that you might ride your bike along as you're moving along the interior park road. This is the turnoff to Lee Lake right here. And if you wanted to go to Jenny Lake, you'd be crossing out this way. And there's some things to see here. You can see the sagebrush and you can see some streams and trees and things like that. When we look at this as a piece of LiDAR and color the elevations along a color ramp, you see something like this. This is the exact same area. And so I'll flip back and forth so you can see that. Okay, I'm flipping back and forth between that so you can see that they're in the same spot. And what you're able to discern in this image now are the multiple paths that the outflow waters from the glaciers moved, or the paths that those the braided streams flowing off of the Yellowstone ice cap carved along the what looks like just the regular flat plain that's up here that we ride our bikes or drive along. And the colors that you're seeing, the brown is the highest. So you're seeing sort of a high platform here where the road goes through, and this is its own piece of sloped outwash deposit. But then that is then dissected, and there was another set of river here and over here at this elevation, and then that then was cut down to creating this small terrace. And then as that was cut down farther, this is a last remnant terrace. And then the last and lowest sort of flow path is this one here that's toward the center. And then this area right here, right, this terrace correlates with this area over here. And so these two sides are essentially linked up and maybe of the same generation. Okay, so I'm going to get rid of all this awful drawing so that you can appreciate the drawing just a little bit more. And I know we're here to look at landslides, but I thought I would show you somewhere familiar in the park that you've probably driven or walked along and thought, wow, you know, that's a pretty boring, you know, pile of brush that's out there. But actually there's a deep history of fluvial process or river process associated with the end glacial period that moved across the plain in the park. Okay. What about something even a little bit more, I don't know, obvious, right? And so in this image right here, you can see the Snake River that's flowing off in this direction. And you can see the active floodplain with the sort of sands exposed and some riparian vegetation along the way. You can see the edges of the terrace, as well as the road right here. This would be if you were heading up that way toward Moran Junction, you'd be driving along that road. And this right here is the turnout for Teton Point, right? So that's what it looks like in the aerial photo. We switch to LiDAR and wow. So, you know, there's all this information that can be gleaned from this. Certainly the floodplain is sort of one broad and very complex set of channels that become activated during high flow periods. Adjacent to it are the greenish, yellowish, higher terraces from a time when the river was not yet incised to the same depth that it is now. And then above that, you can see a paired surface of the old alluvial outwash plain that's in the sort of purple to blues on either side of the river, and that you can see all the flow paths by which past waters moved across those surfaces, as well as where new channels are cutting gullies into the edge of the terrace as it stands today. Okay, so there's some images of sort of areas in the park that you might be familiar with. This is on your way up toward Steamboat. As you're driving along the road there, along Steamboat on your way to Flag Ranch, as if you were going to Yellowstone, and you might go through this area. There's a big burn area that you're probably already familiar with. And as you're rolling along through there, you might not notice too much going on, just maybe some bumpy ground. But if you take a look at this in the LiDAR, you're able to discern something like this, where you can see this great lobe that was sourced from this upper area here that flowed down and is, you know, has moved essentially down and toward the road, right? And so the LiDAR within the park reveals hundreds of features like this that otherwise are not as discernible. And so Josh and Kyla before Josh and myself are working to create a thorough inventory, looking at the LiDAR data and mapping out the positions of the source areas as well as the deposits of these landslides. So we've got in this image just sort of a big picture view of the southern end of the park, and we can zoom in on Black-tailed Butte just for a quick look here. And so on Black-tailed Butte, there are a suite of debris flows that can be visible off the southern side of the butte, as well as some translational rock slides and translational earth slides that are moving off toward the east side. And these are all visible within the LiDAR data. For the debris flows, we map an initiation point, that's the dot. And then from the initiation point, the debris flow moves down the valley. And as it moves down the valley, it accumulates and bulks more and more and more material, ultimately getting toward a lower gradient area where then that debris flow sort of spreads out and builds one of these sort of constructional fans, right? Source area, a flow path, and then sort of a constructional fill area where the debris flow builds out these fans. The same thing is true for the rotational or the translational slides, that there are headscarps where the original failure was sourced from. And these now this is a steep bedrock wall actually in this location. And the material that was shed and translated off of that surface is now deposited down like this, extending out as a lobe onto the plain that's right out here, sort of just south of Mormon Row. Mormon Row is back up this way. All right, again, another rocky headscarp here, and then a depositional lobe extending out onto these outwash deposits that are to the east of Blacktail Butte. Another peek at some of the inventory looks something like this. This is Steamboat Mountain right here. And you might notice a linear feature trending across this particular image. And that traces, wow, what's going on? I'll start at the bottom. There's a linear feature that's down here. This is Jackson Lake. And then you can see there's a cut along the edge of this fan. And that continues all the way up along here where there's this trough that runs along. This is a trace of the Teton. This is a northern trace of the Teton fault scarp. And there's a whole series of earth flows and earth slides that are moving down off of this glacially sculpted terrain with a good cover of till over the top of it. Moving into Granite Canyon, a bit more into the sort of core of the range, you'll notice that this area is dominated by debris flows. It's steep, hard rock, and you can see the source areas as well as the numerous lobes and talus cones that are constructed by the debris that's moving down, either sourced from rockfall or debris flows, building out these cones. Okay. So what do you do when you've got hundreds and hundreds of landslides within the park? How are you going to make use of that? And so this is Josh's workflow that he's put together for his thesis project. He's really got some source data sets like the LiDAR that he's then grouping together into creating essentially topographic data sets that are useful for mapping landslides. Similarly, he's also taking a digitized version of the geologic map and simplifying that down. So he's got that as another geospatial data set. And then on top of this backdrop of a geologic map, as well as the LiDAR data, Josh is going in and making these polygons and lines that basically describe where the landslides are located and what their characteristics are. And we're going to combine all of these observations of where the landslides are to extract topographic information about them. We're going to look for things like slope, curvature, aspect, which way is the slope facing, what's the dominant lithology, and other things like that for the individual mass movement features. And then once we've extracted this sort of topographic character for each of the mass movements, we're going to be doing a number of statistical tests to explore whether or not the types of mass movements that we see are clustered in any particular way associated either with geology or topography. And ultimately from that, we generate three core products. The first one, of course, is the landslide inventory map, which would say, where are the different features? The second thing that we're going to do is the analysis that says, are these features associated with any particular kind of lithology or topography? And that is used in developing any sort of predictive model for where future landslides might occur. And then the last and third output that we're going to be creating is this story map, which is essentially a public-facing data set or a data portal for people to be able to see all of this data. These are what some of the results might look like. These are anticipated or hypothetical results, not actually based off the data that Josh has collected so far. And so we're interested in looking at whether there's some sort of frequency between a particular mass movement type. In this case, this orange color or yellow color are debris flows. And we might expect that there are numerous debris flows in the steep areas of crystalline bedrock. But in that location, we actually don't see any earth flows, right? So you would predict in places where there's crystalline bedrock, you would expect to see lots of debris flows, and you wouldn't expect to see earth flows. The same thing in areas, for example, of glacial till, that you might not expect to see very many debris flows, or rock slides in that unconsolidated, quaternary or glacial deposits. And instead, you might see things more like earth slides, some earth flows, and maybe some debris flows. So this is asking about relationships between the type of mass movement and the lithology that they're positioned on. The other kind of analysis that we might do is understanding topographically, do we find certain kinds of mass movements, like earth flows occurring at primarily lower slopes, and on the steepest slopes, expecting to see more like rock falls and rock slides and debris flows when the slopes get really steep. These kinds of statistical correlations are valuable for being able to make predictions and assessments of where other kinds of mass movements might occur. All right, so some initial findings. One of the things that was surprising in this project was that we found really all major types of landslides present within the park. Grand Teton National Park is not just a bunch of debris flows or just a bunch of rock fall. In fact, you see really an extremely diverse collection of landslides. It's sort of a great place to be able to go see every kind of landslide that you ever wanted. We do see clusters of landslide types that appear correlated with lithology and topography. And so we see that, for example, debris flows dominate in steep crystalline canyons, rotational slumps dominate in glacial sediments and young volcanics. Rotational slides are abundant where there's bedded sedimentary units. Okay, and so this gives you a sense of sort of where we're going with making these connections and having expectations for where future slides might occur. And then in terms of the opportunities that are out there, not only are the possibilities of future susceptibility, risk and hazard maps, but also looking into more conceptually, what are the driving factors between landslides? In a place like the Tetons, the glacial oversteepening created as the glaciers eroded out the valleys and retreated back, leaving unbuttressed slopes. That's one opportunity. Understanding connections between earthquake shaking and landslides. So for example, if we had tools and resources to be able to date when the landslides occurred, we might be able to understand connections between seismicity and destabilization. And similarly, if we knew things about extreme precipitation, would we see landslides clustered associated with wetter or more flashier periods of precipitation? In terms of communicating out our work, we want to be able to use what's called a story map to share these things with the public. And I'll show you some examples of a story map really quick here. Just pop one open. Here is the one called the Bare Earth. And this one was created by the Washington Department of Natural Resources. And in it, they walk you through what LiDAR is. You can see some diagrams I used today. But then ultimately, they get into the application of the LiDAR for doing geologic hazard assessment. And so they go through and talk about what landslides are and how they can be mapped using LiDAR. You can see I've got some similar images that I've shared with you, these ones all coming from Washington. And so not only is there a great example like this that gives us perspective on how to use story maps to communicate these kinds of ideas. And so you can see some of the sort of change that you can detect with the LiDAR. This one for Mount St. Helens in this image. But there's other things that are possible too with story maps. And so here's one that I really like for the Grand Teton National Park. And this one has embedded into it a video. And so we could potentially, be able to show and walk people through what these mass movements look like, or if someone was to get footage of a debris flow or something like that occurring, we could embed that within a story map. And this is a story map that exists for the park. And you can, click through these tabs that are along the top and learn about the resources within the park. And you can embed images, so you can show photos of what the landslides might look like. But one of the things that Josh is really pushing forward that I'm really excited about in our story map, which I'll show you right now, is not only is it going to be informative in the way where we might, show some imagery and sort of talk through a geologic history for the park and what sort of our intention is and what a landslide inventory is, things similar to today's talk. So you might have something like this where you can swipe back and forth between the aerial photo and the LiDAR. But for the individual types, you can click along the top here and be able to learn what a slide is. And then after that, it loads in a map that allows you to zoom in and interrogate all on your own sort of the GIS maps for the park, including the high resolution LiDAR data and our mapping of where the various slides are within this region. And so this is true, and we'll flesh out all of the tabs along here for slides and flows and falls and all the other different types of landslides that will go through, well, what is a flow? Here's an image of an apron generated by a lobe. So here's the deposit, and then going into the map of just the flows. But then the last tab is this fully interactive map. And on this fully interactive map, you would be able to see all of the mass movements that were mapped, as well as some useful things within the park, for example, like things having to do with infrastructure. So, oops, I'll just zoom out. I went in too far here. Okay, that's probably good. All right. So for this particular spot in the park, you can see that all the different slides are now available, and you can turn them on and off. The trails are visible. For example, the trails here around Lee Lake. You can see the roads and the parking areas and the various mass movement features that you might see if you were to, for example, walk along the trail that brings you around into, say, Paintbrush Canyon, walking along this trail right here. So this is sort of our intention when it comes to doing the science communication. We want the product to be both informative and educational to the public and the science community. But we also want it to be, a data set that creates some sort of actionable observations for park management and decision making. And so this is largely what we've got going right now. And with that, I'll call it good and wrap up. And I'd love to have a discussion with as many or all of you. And I was told that the questions are going to be typed into the chat. And then from the chat, I'm happy to answer those and show images of all those kinds of things that might address those. And it looks like Josh has already dropped a link to our preliminary story map as it goes. One special thing about story maps is that literally on the fly, Josh can go in and make adjustments to the map, and those then become available and visible to the public. So for example, if from a citizen science perspective, people were presenting, oh, I just saw, a new rock fall that happened in this area, that could be communicated to the park. The park can then add it to the map. And the map is a living document rather than sort of like a paper publication where you make it once and it sort of has a date stamped on it and it is what it is. The great thing about these online serviceable maps is that they can constantly be added to and improved upon. So that's what I've got to share with you, and I'd love to entertain any questions you might have.
Well, thank you, Dr. Crosby. That was an amazing presentation, very clear. And we do have a number of questions as usual.
Excellent.
Can everybody hear me? Brian, can you spotlight us or something?
I can hear you just fine.
Okay.
You're good,
So
Cynthia.
the first question is, are there LiDAR images of Teton County, specifically the town of Jackson? And I'm guessing that has to do with like a risk map.
Yeah, that's a great question. And the answer, as far as I know, no. There is no publicly available LiDAR distributed through the Open Topography site. That's not to say that it doesn't exist. And my encouragement would be to check with the city, the county, and they, oftentimes those municipalities will fly their own LiDAR for their own management purposes. And so that might exist, but it's not in any publicly available source that I'm familiar with.
All right. The next question is, please explain in more detail the first return, last return method to differentiate foliage from ground in LiDAR. So how does that work?
Excellent. That's a great question. And in fact, I'm going to go straight to Josh's work right here on our story map and scroll through to answer that question. And so in this story map, I think it was right down here toward the bottom, Josh has a really nice image. Is everybody able to see this tree right here?
Yeah, I think we can.
Yes.
I can see it. So I think everybody can.
Fantastic. So what's shown in this image is the red arrow is the laser pulse that comes from the airplane, and it's sent out as a pulse. Bam, it goes out, travels through air, and as it works its way down toward the surface of the earth, anything it strikes along the way will reflect back energy that can be detected by the airplane. Okay, so the airplane both sends out the pulse, but has a detector that receives the reflected energy or light bouncing off of the different surfaces. And you can see that there's 1, 2, 3, 4, 5 different yellow arrows here that are bouncing back up, and it shows the amplitude or the strength of that bounced light. First return, second return, third return, fourth return, and then the last return comes off of the bare ground. And so the instrument in the plane actually receives, for every spot that it sends out to the ground, it receives back 1, 2, 3, 4, up to full waveform of energy that's reflected off of the surface. For the 2014 data in the park, there were 4 returns possible that could be detected. So returns, there's a first return, a last return, and 2 intermediates. And we use the last returns to be able to generate the bare earth topography and essentially remove the trees and the shrubs from affecting what we see, and so that we're able to see the bare ground, to be able to see these landforms.
Oh, thanks for that. That's really clear. Next question is, how well or how effectively are you able to date the mass movement features? that you see in the park?
Fantastic question. Right now, I have not dated any of the mass movements, and that's due to a few different things. Number one, I don't have very much money for this project, and I did have a thank you to the NPS and the University of Wyoming, who provided some seed funding to start the field work for this project, and that's been really helpful in getting us going. But the cost of one or two analyses would be essentially the entire budget of that award. So I haven't done that yet. How would you do that, right? So how do you date the age of a landslide? Well, there's a couple different ways that you could get at this. Number one, if you are able to find where the landslide extends over some pre-existing topography, mowing down maybe some trees or vegetation or burying a soil, if you could see the, if you were able to extract the organic material from that contact where the landslide overrid that organic material would have been living at the time the landslide extended over it. And thus you could say how old, when that landslide extended over that particular spot. Another kind of technique that you could use would actually be to date the material that's sitting on the surface of the landslide. And so you would get an exposure age. And you probably heard about cosmogenic isotopes in previous talks here because they're so important in the park and understanding the glacial history. But if a rock slides, is up here on the side of the mountain, and then it falls apart and it flows down and it creates this big deposit here, that rock sitting here at the surface may now be freshly exposed to radiation from space. And as it sits and is impacted by that radiation, it accumulates over time new isotopes within it that you can measure their abundance and say how long that rock has been sitting out exposed under the sun. And so you can actually say, how long has that landslide deposit been sitting out under the sun? Two things make this process difficult. Number one, it's difficult because it's hard to see underneath the landslide, and it's hard to find those features. And number two, if I were to date the material underneath some lobe of the landslide, or to date the rocks that are sitting on top of the landslide, what's to say that that particular lobe or that particular rock sitting on top of the landslide isn't part of some later stage or some earlier stage? If landslides are recurrent, we would really only be looking at the timing of that particular episode of landslide activity. And that doesn't necessarily tell you when the first movement happened, but it could tell you something about when the most recent activity might have happened or that particular activity happened. So no, I haven't done it. Yes, I want to do it. I would date material underneath the landslide or look at the exposure ages for the rocks that are sitting on top. But
So
I would take the results with a grain of salt, because if it's a landslide complex, I don't know whether it's the first movement, last movement, where it is in the age of those multiple events that are occurring.
So a very related question. Can any of the inventory of mass movements or landslides be associated with earthquake events in the Tetons?
Fantastic. Yes, barely. So the reason why I say yes and barely is because the the Teton fault scarp is the surface expression of movement along that normal fault that's bringing the valley down and the mountains up, right? So in fact, why not just show it? Why use my hands? Let's go to Josh's map here. I was actually right in the right place to show this just a second ago. And I'm going to show you an area right near, right to between Jenny and Lee Lakes. So let's just pop in here. All right, that's a good start. Okay, so in this image, you can see the fault scarp as this sort of shadow that runs right along the base of here. And you can also see that there are a number of different mass movement deposits that mantle over that fault scarp. You can imagine a scenario, right? The earthquake creates a fault scarp, and then a mass movement occurs, either burying or wiping away that fault scarp. And then subsequent, earthquakes that create displacements will offset those landslide deposits. And so it's possible that because landslide deposits cross the fault scarp, you could identify sections where you have young mass movements that remove the scarp altogether, and older mass movements that are actually offset by the fault scarp itself. And so you could say, well, because of cross-cutting relationships, this mass movement, which has a deposit like this, which is then offset by the scarp, is older than more recent displacement along the fault scarp. And there was a graduate student, Kyla Grasso, who focused largely on the fault scarp, who in her thesis discusses the possibility of being able to do this kind of work. But it's a difficult thing to do. Great question, though.
Yep, thank you. And another, I'm kind of skipping around just to keep it interesting, but do you know what the LiDAR coverage is of Yellowstone?
Fantastic question. I do. In fact, in August of 2020, LiDAR was flown for the entirety of Yellowstone National Park. And I've been in contact with and working with the park geologists there to ultimately try to start a similar sort of landslide inventory project within Yellowstone, as well as to make use of that for superficial geologic mapping. And so I've been in conversation with folks at Montana State University that are working on revising the geologic map for all of Yellowstone, including last summer and this summer, and utilizing the LiDAR data as part of those efforts. So great question.
So
it's not publicly available yet, and it'll probably be a while before it is, because they have to do all the QA, quality assessment, quality control first. Sorry to cut you off, Cynthia.
No, that's fine. So we used an amazing picture of a huge slide in Granite Canyon to advertise your talk, but your maps don't seem to show that large feature.
Let's go there.
There you go.
It's in there. If you.
The question was whether you've changed your interpretation, but I seriously doubt that. But let's have a look.
The green body right here is that exact feature. And so you can click on this and it pops up and it says that it is a translational rock slide.
And if anybody's ever hiked Granite Canyon, it is massive and it is so obvious. It's gorgeous if you're into that kind of thing.
Yeah, for sure. And let's see, trying to think of the easiest way to show this. Maybe I'll just leave. You can see all the giant boulders that are here in the LiDAR data. You can see the individual boulders represented right here sitting on top of that feature. And one of the other things that's really special about that is you can see the mass movement coming down and damming Granite Canyon, and there's a big wet meadow complex that exists upslope of that. And so I started with this discussion and I sort of walked away from it a little bit, but the important thing about landslides is that when we think about hazards, and this is something that Bob Smith, who's on the call, has helped me understand. I use his, let's see, where is it? Here it is. For my class on Yellowstone, I use the Windows into the Earth book. And chapter 1 of this is all about the Hebgen Lake slide. And it's really important to think about the associated consequences of a given geologic event, right? So an earthquake can trigger a landslide. Landslides themselves can generate dams behind them, and then those dams can have outburst floods that occur, if the water impounded behind them ultimately is released and able to move down the valley and flood folks significantly farther downstream. And I think if I remember right, Josh, this is working your way down into Granite Canyon. Is there one looking up Granite Canyon as well on this first tab?
So that's Death Canyon from Static Peak.
Oh, okay. Just trying to remember, did you have a view looking back up? Maybe it was on this one. There it is.
Oh, yeah.
So
Nice.
is this the one you're thinking of? The view?
Yep. Mm-hmm.
And you can see that this is the wet meadow that's impounded back behind it, right? So this whole ecosystem would not be here if not for that landslide.
Okay, Ben, we got another question. Are there specific links between the sedimentary formations and landslides? In other words, how do less competent formations competent formations experience more slides? So the link between geology and slides.
Well, that's a fantastic question. I think one of the I think this region that we've been talking about is sort of a great example of that, where you've got in granite, you've got a sedimentary unit that's dipping down toward the valley, and with planes of weakness within that, on what we call a dip slope, more jargon, the rocks are able to slide and translate down. And the same thing is true if you cross over into open canyon. So I'll zoom in here to give a little context for that. Right, okay, so one more click probably would be a good scale to work at. And so we've got sedimentary rocks here that are overlying crystalline rocks that make up the bottom or sort of interior of Granite Canyon. And then on top of those crystalline rocks are sedimentary rocks, which are observable here at the ridge line between open. And then once you cross over into open, there's a whole nother suite of mass movements here that are sliding down and into open canyon and damming that. And you can see these very fluidized flow lines that are moving along the direction that the material is moving. Right? And these are all, again, sliding down on that basically north dipping sedimentary unit. And what's the name of this pass right here? Is it somebody's name between open and granite? Anyone remember? Not like Dave Lewis Pass or something like that.
Hunt's Divide, I believe.
What was that, Josh?
Hunt's Divide.
Hunt's Divide. Okay, thanks. Yeah, so as you move through this area, you walk right beneath, and let me scoot this over so you can see the rock itself. So this cliff right here is the Madison limestone, right? And it's all bedded and dipping to the northwest. And these failures you can see are occurring and leaving behind these broken surfaces of that sedimentary rock as they move in this direction. So that's one kind of expectation, that for dipping sedimentary rocks that you're going to see translational movement that goes down the slope. But another place that is a real humdinger of a mass area mass moves. Whoa, too much. Zoom out. Okay, is up here at the northern end of the park, just south of Flag Ranch. Okay, so this is Steamboat Mountain for reference right here. Here's the road going north into Yellowstone. And you can see this entire blue and purple swath is all one landslide complex composed of many different flows that are moving down and toward the river. And so when you look at this thing, it's just a whole bunch of flowing lobes and headscarps along the edge right here. And this is actually really probably one of the most challenging places to map the landslides, because it's literally landslides on top of landslides on top of landslides. And so, but you can see all the different flow lines and the features moving out this way. And this is an area that has glacial till, but also has the recent volcanic rocks from the caldera forming eruptions in Yellowstone. So it's a combination of both the younger volcanic deposits and the glacial till. Josh, did you have anything to add to that?
Well, we have just a couple more questions.
Yeah, go for it.
If Josh doesn't have anything else. So you've generated a huge amount of interest in LiDAR. And how much does it cost? Because some people are saying, well, could our little tiny geologist of Jackson Hole fund some LiDAR?
Great question. Oh, wow. It's expensive. And if I remember right, and there may be someone else on the call that can help answer this, I want to say it's like $1,000 per square kilometer. And you may say, oh, that's no big deal. I just want to fly a square kilometer. But there's all of these mobilization fees associated with whoever the contractor is coming out to fly it. All right. So how do you get cheap, high resolution topography? There's a couple options. Number one, probably the best trick in the book is piggyback on someone else's project. Okay, so if you find out that the USGS or the county or the park or anybody else is flying LiDAR and going to be developing data, that plane's going to be taking off and landing from the airport. And all you got to do is say, hey, I understand you're flying some stuff in this area and that you want to do this area. Well, can you just do another little area off here to the side? And oftentimes when you're piggybacking on someone else's project, you pay a tiny fraction of the mobilization costs because you're just adding a little bit of data onto that acquisition. That's the best way to go about it, is partnering. The second way that you can go about it is that right now it's possible to mount LiDAR sensors onto drones and fly them. So if you're in an area that allows for drones, it's possible to have really high precision drones that can come and fly. And there are some contractors that are able to do that and provide that. It's still a real evolving thing. The payloads are kind of big. The precision was not as good. You have to have like the Cadillac of drone LiDARs to do this right. Don't buy the cheap one. I'll tell you that because I have lots and lots of friends that have tried to go the cheap drone LiDAR path, and then it just comes out terribly. So you do have to make a really significant investment, good money in, good data out. And then the third option, which is a little less expensive, is something called structure from motion. And that's not LiDAR, but what that is using a drone to essentially do photogrammetry, similar to the aerial photos that I was talking, stereo aerial photos I was talking about earlier in the talk. You fly the drone, you collect some images, and then you can generate a point cloud that makes a high resolution image from that. The downside of that is the first thing that the photo sees is what the topography looks like. So if you're flying it over forest, you'll see trees, not bare earth.
All right. Well, huge thanks, Dr. Crosby. We have a couple of other questions, but I'm afraid we're going to have to cut it off here because we're kind of reached our Zoom limit.
You betcha. I'm happy to give
Uh,
super quick answers if that's helpful to anybody. But anyway, thank you all for your patience and attention, and I appreciate all the questions and ideas. And please feel free to reach out to me if you'd like to ask other questions or if you have other ideas. My email is just my last name, Crosby, at ISU, Idaho State University.edu. So Crosby at ISU.edu. And I love getting email from folks and talking to folks about science. And I come out to the valley all the time because I love mountains and I love rivers and spending time with friends in those places.
Well, thank you again. And folks, if I didn't get to your question, please email Dr. Crosby directly. And thank you again. Fantastic presentation. Loved every minute. Thanks.
All right. Y'all have a wonderful evening.